related. The other one. Oh, I'm sorry.
Good evening and welcome to the Lucille Miller Observatory. We are live tonight and we're going to show you a couple of pictures and talk a little bit about the James Webb Telescope. Our presentation tonight will be presented by Joe Hefner, one of our old members here, and we'll turn it over to him here in just a few minutes. So thank you for joining us and we'll see where we go from here. All right, Joe, you can start. You're going to talk loud and I'm going to cut the volume.
Oh,
I heard that. See?
well, do what? What do you say? I'm deaf in this ear. So. Okay. Oh, okay. So, you have your phones? That's a stupid question. Because I'm going to ask you to do something with your phone a little bit later. You'll see. Thanks for coming. I'm Joe. I've been a member here for 30 years. I retired back in January, so I don't have to do anything anymore. But I still come down here and mess around with all of our kids. Technological toys.
Joe, you're coming across fine. If you're a little louder, it would be better.
Okay.
Yeah.
Okay. We need to get a microphone.
I'm working on it. I've got microphones. We just need to kind of get everybody set up here.
So, what I'm going to do is I'm going to show you some of the images. Well, I'm going to show you all of the images. There are only 5 of them that have been released by the James Webb Space Telescope. I know you all have heard about that. I like him. This is going to be fun. I'm going to. You may have heard some good things. You may have heard some bad things about it. You've probably seen these images on the news. But let me just sort of tell you how old I am. Who in here was alive in 1976? Okay, so something very cool happened in 1976. Anybody besides me remember what it was? Well, it was timed to coincide with America's bicentennial. Oh, okay. Well, the Viking lander touched down on Mars and sent back some of the first Martian images. Now, I'm saying that because in those days, there were no cell phones. There was no internet. The only people on the planet who could see those images were the scientists at NASA. There were no floppy disks. Those images had to be put on magnetic tape the size of a car tire and had to be put in the mail and driven across the country. Everything that I'm going to show you is right here on your phone. Shoot, I can pull them up on my watch. These watches could have taken you to the moon in the 1960s if they existed. So everything I'm going to show you is freely available from various NASA websites. And I say free, your tax money funded all of it. So, and if you're worried about, your money going to, I'll give you your dime or whatever your share was back. If you want it. Most people don't really understand how NASA funding works and so forth. But anyway, some the James Webb Space Telescope, would you believe, was based on 1970s, 1980s technology. This thing has been planned for decades. And I bet you don't know the name of the person who had this vision. It was not James Webb. Anybody in here know who first had the wild idea of these large orbiting telescopes? You know, it's not the first large telescope to orbit Earth. Mike? No, it was not Werner von Braun. Nope. My guess is no one in here is going to know. I'll give you a hint. It was a woman. Wasn't Madame Curie. I really hope the girls remember this. Nancy Grace Roman was her name. And she was an astronomer at NASA. And she said, you know, why can't we put big telescopes in orbit in various places? And people sort of laughed, but we've done it multiple times. She had a hand in designing the Hubble. The Hubble was based on 1960. The Hubble has been planned since the Apollo program. And there are others. James Webb is not the first infrared telescope, and we'll talk about what that means in just a moment. Have y'all ever heard of the Spitzer Space Telescope? My guess is none of you have ever heard of it before, because it wasn't hyped as much. Well, to me, James Webb is cool, but ho-hum, it wasn't the first infrared telescope. Spitzer was launched back in the early 2000s, and if you Google around, you'll find lots of images that were taken with the Spitzer Space Telescope. It has now been officially decommissioned. It has been shut down because these things don't last forever. They have a finite amount of fuel, and believe it or not, it's only supposed to last. I think it's 10 years is the projected mission. Now, to put that in perspective, Hubble was only supposed to last a few years, and it's still going strong. Y'all remember when Hubble was launched? Y'all probably weren't around when Hubble was launched, but Hubble was launched in 1990, and Hubble is still going strong. I think one of its gyros is out of commission, but it's still working. But anyway, someday, you know, it's going to run out of fuel. It's got nuclear power plants on board and so forth. But they're already getting some amazing science back from it, and that's sort of what I want to get to. First of all, let's talk about what it means infrared. What does that mean? Now, if it were a clear night outside, we would be outside with ordinary telescopes, optical telescopes. Okay. Anytime you hear the word optical, for our purposes, you need to think that which the eye can see. Okay. So I see all of you in here because there are particles of light called photons with a pH. Don't confuse us with protons. Okay, these are photons. And they're coming from the light sources, and they're bouncing off of you, and they're bouncing into our eyes, and that's how we see each other. Photons come in different flavors, only we don't call them flavors. In physics, we call them energies. But I'm not going to talk about energy. I'm going to talk about color. So photons come in different colors. We call them red, green, orange, yellow, blue, indigo, violet. You've heard those names. Well, here's the bad news. No one can see all of those 7 colors in a rainbow. That's just made up. Most people can see 3 or 4 at best. Notice I didn't say pink. There are no pink photons. There's no pink light in nature. Now, if I say red, you know what I mean, right? Like that lady's shirt back there. That's red. Okay? If I say yellow, you know what I mean. That shirt right here. If I said green, I see lots of green emitters here. If I said blue, Jeff's shirt is blue. This young lady's shirt right there is blue. What if I said black? There are no photons that are black. Black is the absence of photons. What if I said white? What do you say? What if I said white? Well, there's no such thing as a white photon. But I brought some toys with me. I want to show you something very cool. I happen to have some handheld photon emitters up here with me. Don't even think I had any of those with me. Now, in order to see this, we're going to need to stand up and kind of get within sight of the tabletop here. Now, I said I have handheld photon emitters. That's just a geeky way of saying little flashlights. Now, these aren't ordinary flashlights. These have LEDs in them. That's just a bag. Just joking. Don't pop my phone. I do that. These are LED flashlights. Sorry? Well, I'm not going to give these to you. Oh no, I'm going to turn all of them on. I need a piece of white paper. Oh look, here's a piece of white paper. It's got some writing on it. Here, I'll use this just because it has no writing on it. It doesn't really matter. But now, let's start with this one. Here's a red. We have a couple lights. It's just red. Okay. Would you mind pulling that door out? It doesn't have to be totally dark. Well, I'm building up to that because that's not red. Good guess. But the answer is even more mind blowing. Okay, so everybody see that? Everybody see that? Okay, it's just red. And this is white paper. What color does the white paper look when I illuminate it with red? It's red. Okay. So here's why. Now, I've reversed this. I'm a trained professional. As long as nobody pops my bubble. So white looks white because it reflects all colors. Okay. Her shirt is red because it absorbs everything and only spits the red back. Okay. A yellow shirt absorbs everything but only spits the yellow back. White is just a fancy way of saying whatever I shine on here, it's going to spit it back. Okay. So that white piece of paper looks red because it's absorbing the red light from my light here and it's spitting that back. And you see it does the same thing with blue. And by the way, these LEDs are special because they only emit one particular flavor of photon. Okay? A light bulb, an incandescent light bulb, it emits all the colors. That's why it looks white. So there's blue photons coming back at you. Here's some. Now, that looks blue, but that's actually ultraviolet. Okay, you can't see the UV part of it, but it looks kind of purplish. And let's see. Oh, look at this. Look at this one. Look at that. That's white. Okay, so this one is emitting all of the colors. Okay. Now, I'm going to put the white light over here. Oh, by the way, here's a light. Now, if you listen very carefully, I just turned it on, and it is on. Notice nothing is illuminating the paper. We gotta come up with a better setup for this. But this light is on, and it is illuminating the paper. You just can't see it. I just turned it on. We'll come back to this one. Okay, now I want to show you something very cool. I'm going to take this one, and this one. So I've got a red and a green. Now watch what I do here. Watch these spots. Come over here so you can see this. Looks like orange to me. If I take a red dot and a green dot and I overlap over that, I get some orange. Can all y'all grown up do that? Now, if I take a red and a blue, I get magenta. Okay, so you can mix these. Now, I'm going to put all three of them on the paper at the same time, and I want you to watch what happens. Ready? Look in the middle there. What color is that? It's white. Now, look in the middle. Put your finger right there in the very middle. There, that's white. So you can take these LED flashlights, you can mix all these lights, all these colors together, and you can get white. If you do this with paint, you get what my mother used to call a mess. It's not white. That's because pigments don't behave like photons. Okay? So if you ever take an introductory physics class, you'll learn about the differences between pigments, photons, and how you mix all those colors. So don't go to Lowe's and get one of every color paint and try to mix it because it's not pretty. Okay.
Oh, and here's something else. If you try to add blue fruit color to whipped cream, you'll get green.
If you try adding food color to whipped cream, you've got lots of problems. I hope I never have to find it. Okay. All right, now get your phones out.
Want the light back now?
No, leave the light. All right, get your phones out. Okay, now here's my other flashlight, and I'm probably going to need to walk around. I want you to turn on your camera and pretend you're going to take my picture. And you want to leave the shutter open. Well, actually, you don't want to have the shutter doing anything. Just open up your camera and pretend you're going to take my picture. Okay? Now, this light is off. Okay? So what I'm going to do is I'm going to come around to each one of you. Can I get you to move over here with the other phone? I'm going to come around to each camera and I'm going to turn this light on and then off. And I want you to watch your phone as I do this. Okay? Ready? Now, those of you who don't have a camera, you're going, what the heck are they looking at? Because I don't see anything. Okay, you move, son. Now, that's weird. I saw your screen here was really bright there. Now, watch. I'm going to do the same thing. Everybody look up here. Ready? Off. On. That's off. Nope. I'm just aiming it. Kind of down. I'm aiming it so that if it were on, it would do this. Okay? But it's not doing that. But your camera proves that there is something coming out of it, right? Now, I'm going to show you something else. Watch, look at it. What do you see? It's red. Okay. That was infrared light. Now, this chip that you saw, that was red. That was not infrared. I cannot tell you what infrared looks like because the human eye can't see it. But the chips in your cameras can detect it. Now, when I say see, and I really shouldn't use that word. I really should say detect. Okay? Because the particles that make up infrared are the same as the particles that make up these other colors. It's just that our eyes aren't sensitive to it. And it's redder than the reddest red you can imagine. Infrared. I can't describe it because our eyes can't see it. But the chips in your phone can see it. Now here's your homework assignment. Go home and take the remote to your TV and look at it with your camera when you change the channel. You will see the same thing because TV remotes use infrared. Okay. So your eyes see nothing. Your detector tells you there's light coming from this thing. Okay? And just like there's more than one color of regular photons, there's more than one flavor of infrared photons. There's near infrared, there's middle infrared, there's far infrared. And this is going to be important when I show you these images. Okay? Any questions so far? By the way, please, I'm a retired college professor. Ask questions. If students are silent, it means they're probably buying stuff on Etsy, whatever. So just talk. If you have a question, ask it. Okay. Any questions so far?
Why are we talking about infrared?
We're talking about infrared light because the James Webb Telescope is an optical system that doesn't detect visible light. It only detects infrared photons. If you need to. The Hubble Space Telescope is an optical telescope. And by the way, it's the last optical telescope that will probably ever be put into orbit. Okay? We've pretty much done all the science that can be done with an optical telescope. And that might be a bit of a stretch. But NASA's kind of done with optical. Okay? And turns out that infrared, we're living right now through what a lot of people call a golden age of astrophysics. Just since the 1990s, we have learned so much about the behavior of the universe. When I was in college in the 1980s, taking my astrophysics courses, we knew that the universe was expanding, but we could not tell you the rate at which it was expanding. The number was 50 plus or minus 50. Those of you who know what error bars mean, that's horrible. Okay, and I'll explain more about what that number I just quoted means when we look at these images. But since the 1990s, all of the textbooks in cosmology have been rewritten. There are people right now, because of that image right there, rewriting the astrophysics textbook. There are people studying that image for their PhD research. You're going to see that image a lot. Somewhere on the planet, there are PhD students studying that image. Because that light that you see is infrared light. And by the way, that image right there, you took a grain of can't remember if it was rice or sand. No, it's sand. If you took a grain of sand, hold it at arm's length, that's how big that patch of sky is. Let me say that again. You take a grain of sand and hold it at arm's length, that's how big that patch of sky is. So let's talk about this image. This was the first image that the James Webb folks released. It's called a deep field image. You may remember back in the 90s, the Hubble people released the Hubble deep field, and then several years later, they did the Hubble ultra deep field and so forth. Okay, this is the modern version of it. Just to put this in perspective, the Hubble deep field took days of exposure time. This was done in about 12 hours. Several days of exposure time versus 12 hours. That's how far the technique has come. You cannot see this with an ordinary telescope. One of the telescopes here that we have, Hubble, cannot see this. You are picking up infrared. Now, somebody already said, well, I see white, I see blue, I see orange, I see gray stuff. Well, that's because a human processed this image to put those colors in there. Okay? Because remember, the human eye can't see infrared. Okay? So whoever takes this image, they can make any flavor of infrared light, any color they want to make it so that it looks pretty to the human eye. Does that make sense?
So first color they use it to do. That's what you see on your little radar maps.
And so it kind of bugged me the other night when I heard a NASA person named Klaus, I'll never forget that name. He answered a question from a layperson. The question was, are these colors real? His answer was, of course this is real. Oh, no. These are false colors. These were put in by the person doing the image processing. The human eye can't see these colors. You can't see the infrared. And by the way, I forgot to tell you, you are emitting infrared. Everything around you is emitting infrared. If this were January, I could ask you to sit really close together and almost touch each other. What would you feel?
This one, no.
You ever been cold and you snuggled up next to someone? Okay, we call it body heat. It's infrared radiation. Okay, everything in the universe, this box, this table, the chair, this thing right here, everything is emitting infrared. Those were all. Now, that image, oh, it absolutely is beautiful. But astronomers, how should I put this delicately to keep from further being ostracized? Astronomers don't look at this for the prettiness of the picture. What they do is they want to know, for example, let's take that galaxy right there. They want to know how the light varies across the face of that galaxy because they can turn that into information like, is that galaxy rotating? If yes, how fast is it rotating? Is that galaxy coming towards us or away from us? If so, how fast? Yep, I'm going to tell you exactly what those are. I'm going to tell you exactly what they are.
Well, there's scientists will assign certain colors to certain chemicals. If you see reds and a lot of these things, that indicates that they've got a lot of hydrogen. You see green, it's 91%, you've got free oxygen out here. And other colors, they can pick any color they want to. And they just pick certain colors to represent certain flavors.
And astronomers don't have to have a color image to do their get people to want to give NASA more tax money. You think I'm joking? I have not seen the unadopted version. In grayscale. Grayscale. What happens is the detectors, well, in this case, you've got gold-covered mirrors, gold-covered beryllium mirrors. I'm not going to go into all the engineering, I don't understand it all. But ultimately, you've got gold-covered beryllium hexagonal mirrors. And that's why you see 6 diffraction spikes there. Everything with spikes is a star. Okay? So that's a star, 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 that. If it's spiky, it's a star, and it's our galaxy. Okay? Now, stars, depending on their temperatures, may be visible in the visible part of the spectrum. So it could be that Hubble could see some of those stars. If they are very cool stars, Hubble would not be able to see them. Those very cool stars emit mostly infrared. The Earth emits infrared. Planets emit infrared. And if you look through the news headlines today, they released a Jupiter image today that shows Jupiter in the infrared. It's gorgeous. It is gorgeous. So the spiky things are stars. Okay? And 6 spikes, and if you look very carefully, there are actually 8 spikes. There's the little one there and the little one there. And those are just artifacts of the optical system. If you see an image where the stars have 4 spikes, that's a Hubble image. If you see 6 spikes, it's a Webb image. So automatically you know which observatory took the image. Okay? All right. So what are we looking at here? Everything that is not a star, everything that is not spiky is a galaxy. Now, in case you don't know what a galaxy is, let me tell you. A galaxy is a group of stars numbering in the trillions. See, that number really doesn't mean anything. So, a group of stars in the trillions that can be flat like a pancake with spiral arms. Look at that one right there. We live in one of those. We can't see it because we're inside it. But every star in this image is in our galaxy. Every star in this image is in our galaxy. Okay? So when you go outside on a clear, dark winter night, all those dots you see are in our galaxy. Okay? Each one of those fuzzy things, okay, so things are either spiky or they're fuzzy. If it's spiky, it's a star. If it's fuzzy, it's a galaxy. There are thousands of galaxies in this image. Now, big deal, because if you look at the Hubble deep field, everything in that image is a galaxy too. Why are these galaxies more special? Here's the reason. These galaxies are so far away. I knew he was going to do that. I know that you could have warned me that he was going to do that. We need you down here more often. Yeah, these things are so far away that the light that they emit is stretched. And you know what happens when you take light and stretch it? Now, I'll tell you how to stretch light in just a moment. But do you know what happens if you what happens to a rubber band if you stretch it? I heard 3 different answers was the one I was looking for. So suppose you don't let go of it. Suppose it doesn't break. Somebody said it gets thinner. That's true. What did you say? Okay, let's pretend it doesn't break. It gets longer. Okay, so here's the thing. When you pull light, it gets redder. Don't think too hard about that, because that's difficult to explain. Okay? But if you pull light it gets redder. So it is possible to take blue light and stretch it out into red light. Good guess. But why stop at red light and stretch it even more until it becomes so red that you can't see it anymore? It becomes infrared. How is this light being stretched? It's because the space that the light is moving through is stretching because the universe is expanding. You ever been to an airport? I got stranded. The very first time I ever flew, I got stranded overnight in O'Hare in Chicago. Loved it. Had to run in the place because it shuts down at night. Everybody goes home. And I had free run of the place. It's the safest place in the country to be. You're behind security lines. Nothing can get to you. So what did I do? You know those moving sidewalks? I played Expanding Universe. With Pink Floyd music playing in the background. Psychedelic light shows on the top. So you know those people movers that we're talking about there? Okay. So you know that if you're standing on the floor and somebody gets on the people mover next to you, if they just stand there, that people mover is going to take them on down the line, right? You know what I'm talking about? It's like people movers are conveyor belt. I got the feeling I'm losing it.
Yeah, I've seen those and never been.
You need to get on one of them.
I don't know where it is.
You need to get on one because they're so cool. Because, okay, so now imagine you standing here and you hold one end of the rubber band and you give the other end to the person on that sidewalk, on that moving sidewalk. What's going to happen to that rubber band as the people mover? It's going to get stretched. Okay, the conveyor belt is the expanding universe. Don't take that literally because you can't picture the expansion of the universe because it's not expanding into anything. But imagine that rubber band being light. Okay, the further away the people mover takes the other end, the longer that rubber band, the longer that light is going to be, and the more infrared it's going to be. Hubble can't see these galaxies. Their rubber band has been stretched too far. We had to build a telescope to detect them. This means they are very far away. They are also very young. These potentially could be some of the first galaxies to have formed after the Big Bang. Hubble can't see these because Hubble can't see in the infrared. Now, there's an infrared camera on the Hubble platform, but the main instrument itself is not an infrared detector. It's an optical visible light detector. About the size of a school bus. This is bigger. The light shade on this thing is the size of this. So, you are looking at things that are so far away, the expansion of the universe has stretched their light into the part of the spectrum that our eye can't see. That's why people are so excited about it. So, those orange things, what do they do? I'll be honest with you, when I saw that one, I thought of a tadpole. I thought of a tadpole. But now, if you look, there's a pattern to them. You just stand there and go, that's, your brain is good at detecting patterns. There's swirliness. Okay. It looks like they're at the rim of a circle. Right? And notice that there's a big old fat galaxy sitting there. This is called a gravitational lens. Einstein predicted this back in 1915, 1917. People laughed at him. We knew in the 90s that he was right. And here we see these. That is the second, after noticing the tadpole thing up here, I thought, look at all of those gravitational lensing arcs. Each one of those arcs is a galaxy that is behind that galaxy right there. And the only reason we see it is because that big fat galaxy in the middle there is curving the space-time around it so that it acts like a lens. It is curving that light into our field of view. It's called a gravitational lens. And Einstein wrote down the equations that describe all of this. You are seeing space-time curvature in this image. What was the year? He published his first paper on general relativity in 1915. I'm going to say the late teens. It took a while. It took people a number of years to learn. Einstein took 10 years to learn a whole new branch of mathematics. So don't feel bad if you don't, pick up math right away. It took Einstein 10 years to learn differential geometry, which is a lot harder than your multiplication table. But even every brilliant scientist had to work hard to learn whatever it is they learned and know. That includes Einstein. So oddly enough, if I were your teacher, I could teach you a lot of it in just a couple of years. Because it's not that bad. But back in the early 1920s, it was a new branch of mathematics. Anyway, so if we were to take away that galaxy, we wouldn't be able to see. First of all, those arcs would go away, and we would not be able to see those galaxies. The only reason we see them is because there's this big, massive galaxy in front, and it's bending the light around it. We can see them. And cosmologists can actually measure those rings. They can measure the curvature and the thickness of those rings. They can work backwards, and they can tell you everything there is to know about that galaxy. And they're just all over the place. They're just all over. You can see that in a. Well, this was the first image. This is now my background image on my computer at home. I just love looking at the spiral galaxy there. That galaxy right there doesn't have spiral arms. That's an elliptical galaxy. It's like an egg-shaped galaxy. That thing right there, that's an irregular galaxy. Galaxies come in different kinds. And so you could easily spend an hour just looking at that image. I don't know because I haven't been able to find the color coding. I don't know what scheme was used. No, because all of these are redshifted. These are too far away to display blue shifts. We're seeing the expansion of the universe here. It's real, y'all. It's not just textbook. It's real. I don't know the number. I don't carry numbers around. It's not in Earth orbit like the Hubble Space Telescope is. It's out at a place between the Earth and the Sun. It's so sensitive that if it were to look at this Earth, it would fry the optical system. If it were to look at the sun, it would fry the optical system. That's why it has these shades on it that block. And the detectors that detect infrared light, they have to be cold. So y'all may remember this thing was launched on Christmas Day. Since early March, when it got to its home place out there, it's been cryogenically cooling down to just a few degrees above absolute zero. The web is. Yeah, it's in a place. Not quite. Okay, so. No. Okay, so. Okay, let's pretend that's Earth. Okay. The Hubble Space Telescope is 250 miles long, and it goes once around the Earth every 90 years. Yes, it's facing out. You don't want it looking down at us. No intelligent light. Between the Earth and the Sun, okay, so there's Earth, here's the Sun. There are places in space called Lagrange points. So you have to say Lagrange points. Okay, there are 5 of them. There's one here, there's one here, there's one here, there's one here, and so forth. Okay? You can work out mathematically where they are. Those places are basically places where the Earth's gravitational field and the Sun's gravitational field will allow it. And you can put an object there and it will stay there. It wiggles around a bit. It won't go flying off of it. Okay? Yeah. Gravitational. Okay, and so you have to keep it oriented so that it doesn't look directly at the Earth, because that will fry the sensitive optics. You don't want it looking at the sun, that will melt the sensitive optics. It only has a very small range of sky that it can see. It can't see the entire sky. It can't see the entire sky. Remember, this is a grain of sand. And so it's at that Lagrange point, primarily so that it's not affected by the warmth of the Earth. Remember, the Earth is an infrared emitter. That's why it took March, April, May, June. That's why it took 3 months to cool this thing down. Any heat shows up as noise in the data, and you don't get the images. It has to be very, 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 very cold. Okay, I'm talking too much. I'm going to show you the other 4 images. There. Say again? How far away is that? The stars or the galaxy? Okay, so the stars are in our galaxy, so they're within 100 light years. I would have to look up what stars those are, and I would have to look up whether we know anything about those stars and how far. They're only others that we have data on. Now, I'm so old that I can remember when that number was 1,500. When I started out in the 1980s, we only had good distance data for about 1,500 stars. Now it's in the millions, thanks to the Gaia data release that was just made, the Arcus data release back in the 90s. The galaxies, you're talking billions and billions of light years. So you're seeing light that has taken millions of years to get here, if not billions of years to get here. The universe is 13.7 billion years old, but these things are farther away because, remember, the space has expanded. So you got to be careful when you use the word distance in astrophysics. Distance has no fewer than 5 or 6 different meanings. Depends on whether you're accounting for the expansion of the universe, whether you're talking about light, or whatever. Distance is a very fishy word. You have to be very particular about how you define it. But millions and billions of light years away. The stars within 100,000 light years away. They're in our galaxy.
So would it be safe to assume some of those things aren't there right now?
It's possible. I mean, that's a question that really has no answer because in 1905, Einstein published his special theory of relativity. Okay, I promise I'm going to get to the other thing. But in 1905, Einstein taught us that the word now has no meaning because now here and now on the sun are 8.5 minutes different. When you say, what's going on the sun now? You've got to say, our now or their now. How now? You see, this gets very, very, very confusing. And the words are really important. So now on these galaxies is not the same as now here. Because we're seeing them as they were billions of years ago. And we can't know what's going on there now. Because our now and their now are not the same now. Now, I'm gonna okay. Now, this next one. Okay. Now, this is not a star. This is not a galaxy. This is a spectrum of an object called WASP 96b. We're idiots when it comes to naming these things. I've not looked up what WASP stands for, but I will tell you that WASP 96b is a planet around another star. I don't know what he said. Well, that's what I was thinking, but I wasn't going to say it. You said the quiet part out loud. So this is a planet comparable in size to Jupiter. It is orbiting its parent star every 3 days. Every 3 Earth days, this thing goes around its parent star. And this is a spectrum. A spectrum is what you get when you point the business end of a telescope detector at a star and you gather all the various types of light that thing is emitting. And the spectrograph sorts them for you. And it can produce a graph called a spectrum. Now, if you remember from your chemistry, different elements have different spectral fingerprints. And what's interesting here is that we are seeing the signature of water. Why is that important? Got to be careful. Life as we currently understand it. We are very arrogant in assuming that if there is life out there, it's got to be like us. No, do not. Have you noticed in all of the movies, almost all of the aliens have one thing in common. They look like us. They have arms, heads, legs, thoraces, bodies. They have mouths, sometimes 3 or 4 mouths that come out of each other. It scared the crap out of me when that movie came out. Yeah, they all look like us, and that's because the human mind invented those aliens. Okay. So astronomers are excited about this because they did not expect to detect this water vapor. This is water vapor in the atmosphere. These are clouds in the atmosphere of this planet. Now, this spectrum is inverted. The way an astronomer would look at this is everywhere you see a hill, we would turn it upside down, we would see a dip. It's called an absorption. So what you're seeing here is the presence of clouds in the atmosphere of this exoplanet. There are clouds in that planet. We know those clouds are made of H2O. There you go. You can't even, I don't think you can even see the star with the naked eye. I really haven't looked that up. But look at these wavelengths. These are infrared wavelengths. The human eye cannot discern this light. You got a question, or you just do it? Oh, all right. And the blue thing here is a computer model that fits the data. See, they've been working on this since May. And you can see that the white dots are the measured data. The blue is a computer model. You can see it's a pretty good fit. That means it's real. And they didn't expect to find this. They were shocked. Shocked, I said. Now, in prison, Bob Eskridge right here has seen this thing through his telescope. This is called Stephan's quintet. What does quintet mean? Five. Okay. There are 5 things in this image. 1, 2, 3, 4, 5. Okay. Yeah, there's one right here, but let me tell you about. I'll come back to this one in just a moment. Okay. That one, it turns out. Well, I'll just tell you now. It's not part of this group. Okay. It just happens to be along the same line of sight. You look very carefully at these two. They're hugging each other in a galactic sort of way. They're merging with this guy and this guy. This guy is not at the same distance as these 4. It just happens to lie along the same line of sight. So here we have 5 galaxies, I'm ignoring this little one, 4 of which are physically interacting. And this object is in Pegasus, I believe. In principle, we've got a telescope out here that could show this to you. Now, it will not look like this. The galaxy, you will not be able to see the structure in the galaxies, but you can discern them as galaxies. They are not stars. Stars look spiky through a telescope. Okay? Fuzzies do not look spiky through a telescope. But this is not light that our eye is sensitive to. Remember, this is infrared. Okay? And by measuring various things about the light, we can tell that, yes, those galaxies, they're not only spinning, they're ripping each other to shreds. Look at all this stuff here. That's galactic guts. But we think this is how spiral galaxies work. And we have evidence of this because there are places in the sky where you can look and you can see galaxies that our galaxy has digested. I'm not going to have to separate you two back there. It's like freaking fun. I think you're both egging each other on back there a little bit. Like, did you hear what he said? Yes, exactly. And there's the butthead right there. I lost my train of thought now. I was thinking, yeah. Yeah. So our galaxy, they're called streams, and you can find these galactic streams that are evidence that our galaxy has literally digested other galaxies. This dates back to the 1990s. This is new stuff. And no 2 stars will touch each other as these collisions happen, because most of what you see there is empty space. I'm just going to try to egg them on. But this guy is just an interloper. It just happens to lie along the line of sight. It is not part of that physical system. Look at that right there. That just, like it's sucking up a milkshake or something. She's like my college students. I put many of them in with leaving. I was just getting ready to go to the interesting.
And I'll tell you what, we'll have this on our YouTube channel, and you can go back and look at it. Fast forward to the rest of the presentation.
I sound good at 2X. Put some Benny Hill music in the background. So here's another one that they released this week. This is part of an object that from our location here on Earth. This is part of the Carina Nebula. And if you look at this, it looks active. It looks turbulent and boiling. That's because it is. You're looking down inside a big cloud of hot gas and dust, and you're seeing baby stars forming. Look at all those spiky things there. This is in our galaxy, by the way. And so, and here's the thing with infrared. Infrared can see inside clouds of dust. Optical light can't get through. Hubble can't see these things. The pillars of creation, Hubble couldn't see inside of those gaseous columns. Webb can. Spitzer could see down inside of them. The best Hubble could do is see the baby stars emitting their light over the top of the pillars. If you look at the image, there are actually some embryonic stars. They're peeking out from their blanket. Okay. We're looking through the blanket here. This is all infrared and has been color coded by the people who process it. And you know, these little bumpy places, that's where you're likely to find stars that are in the process of forming out of collapsing gas clouds. Now, this object is visible to the naked eye. Whoa, boy, did I make a mistake there. It's not visible to the naked eye. It is visible in telescopes. But again, this is not visible light. This is infrared light that you're seeing here. So this particular view, you can't see into the cloud with an optical telescope. You just can't do that. Have you seen it?
Where is that?
Ada Carina. Now, I think this is the last one. Yep. Okay, now this one, okay, this is the south. Now, when I saw this one, the thing on the right, I immediately thought, well, that looks like a piece of country ham. So I call that the Country Ham Nebula. You heard it here first. This is an object called the Southern Ring Nebula. If it were clear outside, we could show you the Northern Ring Nebula. Yes, it's the same image. Yep. Captured in two different flavors of infrared light. The one over here is near infrared, nearing. This one is nearing, middle infrared. Okay, so think of this as dark red and light red. Okay, even though that's not the best analogy. This is just one particular flavor of infrared. This is another particular flavor. But I want to call your attention to this. Oh, by the way, and this is a planetary nebula. This is in our galaxy. So that spiky thing, that's in our galaxy. This is what our sun is going to do in about 10 billion years. Our sun is going to basically end up looking like this. But I want to call your attention to something. Look at that, and look at that. There are actually two stars there. The star that is in the process of dying is that one, that little one right there. I think they said that this is a foreground star. They told me to do that. They said, it means it's not part of this complex. But notice that the progenitor star is not visible here because it's not emitting any of the light in this part of the spectrum. Only this wavelength is being picked up from that star. Okay. This is why you need detectors that can detect a wide spectrum, a wide range of infrared colors. Like I could give you 10 flashlights. They could all be red, but they would each be a different shade of red. That's kind of what's going on here. Only instead of red, it's in blue. Okay. And that's a galaxy, I believe. That's an edge on a galaxy. It just happens. Now, obviously, if that's a galaxy, that's millions and billions of light years away. It just happens to be in that particular direction. I don't know what this looks like through an optical telescope. I had never heard of this object before. I don't even know if it's visible from the corner. But look at this star here. Notice this star, at this wavelength, it's not putting out nearly as much light. Okay. It's putting out much more of the light in the near infrared part of the spectrum. That tells you something about the properties of that star. It tells you something about the temperature. Also notice there's a really red object right there. That's probably a background galaxy of some sort. And there's just a lot of structure here. Now here's the cool thing. They can come back next year, take an image of this same object, and those swirls will have changed. This thing is expanding outward. It's moving. It's moving on time scales of years. And if you look at it in enough detail, you can see those knots of material moving. So that's the country ham. I don't know what that looks like. A burnt pancake. A lake. Okay. You got a lake and you got that's country ham. Okay. All of these images are available from the NASA website. If you Google NASA first web images, they're all available right here. I just downloaded them. They're free. They're paid for. Your tax money paid for them. They're yours. I do not. I don't think they've actually posted it to the website. I follow contacts that I know, like for example, I know Heidi Hamill, who is actually one of the persons who built the darn thing and is actually using it. She's a planetary scientist. She got her start back in the 90s with Shoemaker BB9 when the comet smacked into Jupiter in 1994. She was a young scientist then. So actually, she sort of leaked the Jupiter image, and that's where I saw it. And she's royalty, so she can do whatever she wants to. But when I checked as of about 6 o'clock tonight, it had not been on. Oh yeah. It's checking back periodically. If you Google Webb Jupiter, you'll find it.
Now, one thing I want to once you see what you get, astronomers will never think any part of their image. If somebody comes to me and says, if you look carefully, you see the face of Jesus, and no, that's not an official thing.
And if you see a plate of country ham and they try to tell you that it's a space object, now these images are large, but that one, I have a 21 and a half inch monitor, and it fills it up. And I just sit there going, I mean, yeah, they released this one last week. This is the one that the president, the vice president, no, I say last week. It was Monday or Tuesday, and then they released the other 4 at a another president. Anyway. So that's all I was going to say. If y'all have any more questions, I'll be glad to answer them. I want you to do the little camera activity with your remote control. Remotes use infrared LEDs.
Here's something else that you can do. Because you sound on, you're going to feel it before you see it coming. That's it.
And then you can cook a piece of country ham. Bread, red-eye gravy on it. You got breakfast.
Thank you so much.
You got to stay up late to be astronomers. It is almost 10:25.
Thank you all, ladies and gentlemen. The video will remain up there, and if we have more information coming out, more programs, we'll get them out there. Our next broadcast will be on Friday, the first Friday in August. So please join us at around 9 o'clock. Have a great evening.